Okay, next up is number 30. A 0.65 meter long metal bar is pulled to the right at a steady 5 meters per second perpendicular to a uniform 0.75 Tesla magnetic field. The bar rides on parallel metal plates connected through a 25 ohm resistor, so the apparatus makes a complete circuit. Ignore the resistance of the bar and the rails. Part A, calculate the magnitude of the EMF induced in the circuit. Alrighty. So, our EMF is minus d by dt of our magnetic flux. Boop, boop. So our magnetic flux is B field times area our area is length times width. So in this case, this is our width. Boop, boop. Boop, boop. Now this width can be written, or this width is going to change as we're pulling this bar along, because we're making the area that's induced, or that's going to induce a current, bigger by pulling this bar along. So W, we can write as velocity times time, because as we're pulling this along with the speed v, we're increasing the distance according to velocity times time from good old kinematics 1. Alright, so our time derivative, b is constant, L is constant, v is constant. So our time derivative is going to give us minus b L v. So if we punch that into our calculator, 0.05 Teslas. Length of our stick is 0.65 meters. And our velocity is 5 meters per second. Our induced EMF is 2.4375 volts. And the minus sign is just there to tell you the direction, so we're not really going to worry about that. Okay. So, next part B, says find the direction of the current induced in the circuit by using 1, the magnetic force on the charges in the moving bar, 2, Faraday's law, and 3, Lenz's law. So for part I, using the good old F equals QV cross B doodad. So we have our charges inside this little bar. So as we're pulling this bar to the right, we're also pulling all the little charges to the right with it. So our velocity is that way. Our field is into the page. So from QV cross B, they're going to feel a force upwards, assuming they are nice, happy, positive charges, which is what we assume for conventional current. So if we're pushing our positive charges up, that means our current is going to go up and around that way or counterclockwise. Okay. So for Faraday's law, that's our EMF equals minus d by dt flux B. So our flux is currently into the page, and as we are pulling our bar out, we are increasing the flux. So it's getting more into the page. So the negative change in flux is out of the page, which is going to give us a current that way. So to summarize, our flux is into the page. Our change in flux is getting more into the page. So our minus change in flux is out of the page, and right hand rule counterclockwise. All right. Okay, so from Lenz's law, that's when we're looking at what the field is doing. So if we have our big beautiful picture, we have a bunch of x's in there. As we're pulling this bar to the right, we are increasing the area. So we're letting in more magnetic fields. So we're increasing the flux. Nature doesn't like to change. So in order to cancel this out, if we have 4 extra into the pages, we're going to cancel them out with 4 out of the pages. So that's what we're going to induce. So we're inducing out of the page, and that's going to give me a current counterclockwise. Huzzah! Alright, so part C, calculate the current through the resistor. So we have the voltage, we have the resistance. So good old V equals IR. Tells me that my current, V over R, is 2.4375 volts over my resistance, which is 25 ohms. That's going to be 0.0975 amps. And that's it.